So you're up like, can you tell me how to project my screen? Oh, yes. Okay. So we'll go ahead and do now. We'll review stuff from the videos yesterday, and then we'll go through some examples. So today we're going to focus a lot on calorimetry. Tomorrow we'll focus on Hess's law. So today we'll look at both coffee cup and bomb calorimetry. Then you guys will have some time to do practice, and then we will look at Hess's law tomorrow, examples and practice. So for number one, if a 10-gram sample of each of the four elements in this table is heated and placed into a container of water, which element's container would show the greatest increase in temperature and why? And I said think about the units and what specific heat means. So I gave the specific heats for each one of these. The units for specific heat are joules per gram degree Celsius. So when we look at specific heat, we're putting the same mass into each of the containers, so the same mass of each of these metals, and we're heating them the same amount. So we're putting the same amount of energy into each one. We want to know which one would show the greatest increase in temperature. So if you're putting the same amount of heat into each one, really we're looking at either the highest or the lowest specific heat. So we can ignore copper and nickel. We're either going to look at aluminum or lead. So we either want the highest specific heat or the lowest. Well, if we want the greatest increase in temperature, we actually want the lowest specific heat. So we actually want to look at the one with the lowest specific heat. So the greatest increase in temperature is going to be lead. And the reason that it's lead is because if we apply the same amount of energy, this only takes 0.129 joules to heat 1 gram by 1 degree Celsius. Aluminum takes 0.9 joules, about 8 times as much. So this takes 0.9 joules to heat 1 gram by 1 degree Celsius. The lower the specific heat, the faster the temperature changes. So the reason, greatest increase in temperature is lead because it has the lowest specific heat, so it does not take much energy to change the temperature. That's why we use metal to cook. Right? Typically we use metal pans to cook on the stove because they heat up much more quickly than glass, ceramic. And then that's also why in the specific heat lab, the temperature of the metal, so we looked at lead and copper, the specific heat of the metals changed, or I should say the temperatures of the metals changed a lot more than the temperature of the water because they have much lower specific heats than water, which is 4.184. And then number 2 is a hot bowl of soup, an open system or a closed system, and explain your answer. So this is not a trick question. If I have a bowl of, let's say, tomato soup, and I put a bowl of tomato soup on the table, is that bowl open or closed? It's open, right? So an open system is something where heat can escape. A closed system would be if I put a lid on it. If I put a lid on it, heat cannot escape, or it shouldn't escape. So for number 2, it's an open system. Our reason is that the container is open and heat can escape. Great, so that's it for the do now. Today we are going to go through lots of examples, so you want to make sure you have a calculator. If you want to use your phone today as a calculator, that's fine. But as long as you have a calculator, and then go ahead and get out your notes. So the notes today, the examples start on page 10. We are going to just kind of do a quick review of some of the notes themselves on pages 4, 5, and 6. So while you guys are getting your notes out, I put lots of questions from the videos on the next 2 slides. So the first video, which was 2.3, so I should say the first of the two from yesterday, 2.3 was still pretty conceptual. It was talking about enthalpy. It's talking about enthalpy. So enthalpy is delta H. So if you say delta H instead of enthalpy, that's fine. Enthalpy is just the heat gained or lost during a reaction. Enthalpy is another term for heat. So we'll talk about how delta H and Q are similar, and a lot of this is just pulled right out of the notes. But enthalpy is the heat that's gained or lost during a reaction. In the video, I showed how delta H was derived, looking at delta E and the idea that P times delta V is work. We will always perform our reactions at constant pressure, so we do not worry about the PV work variable. I'm not going to ask you to calculate using that P times delta V. We are going to just worry about calculating delta H like we will look at in the examples, using the idea of Q. So we assume that delta H equals Q. They are essentially the same. The units are different. We'll look at how we calculate them in various ways. So today we're going to focus on calorimetry. Tomorrow we're going to look at Hess's law. And then next week we will look at 2 additional ways to calculate delta H. So when we talk about enthalpy of reaction, that's delta H reaction. That is truly just calculating the enthalpy of a given reaction. So it's, again, how much heat is gained or lost. Here's where it becomes a little bit different from Q. Q is just joules, or maybe kilojoules. Delta H is always joules per mole or kilojoules per mole. So we're looking at per mole of something. That's where the difference comes in. So when we say that delta H and Q are essentially the same, the only difference is that Q is for a specific amount of something. We're going to look at this idea of the units being different today as we calculate delta H. Q is for a specific amount. So when we looked at the specific heat lab, you guys calculated Q for a specific amount of water and a specific amount of metal. Delta H is kilojoules per mole. So as long as we have the same reaction every time, delta H should be the same because it's kilojoules per mole. So when we're looking at calculating, we're always going to look at the units to determine what we need. But we'll look at how to tell whether it's calorimetry or whether it's Hess's law. We will look at that more and more over the next week. So that was another question is, how do I know if I'm calculating delta H or if I'm calculating Q? They're basically the same thing, it's just what units do they want. So as we continue to look at enthalpy, right, delta H, we can use the idea of delta H just like we can with Q to figure out if a reaction is exothermic or endothermic. Exothermic, remember, heat is released. Heat exits the system. So delta H is negative, Q is also negative. When heat is absorbed, it's endothermic, so delta H and Q are both positive. So the way to tell if something is exo or endothermic is to look at the value of delta H or the value of Q. Now going along with exo and endothermic, we can also look at phase changes. Phase changes meaning freezing or melting, condensation. Where are we going from one state of matter to another? Now, the exothermic or endothermic depends on what is happening to the particles. And you'll look at some in the practice today, but the phase changes depend on the particle motion. Do they have to speed up or do they have to slow down? That should be the question that you ask yourself to figure out if a phase change is exo or endothermic. So if we think about melting, I put an ice cube on the desk, melting is going from solid to liquid. So I just have to ask myself to go from solid, where the particles are pretty close together, just vibrating in place, to a liquid, where they're moving a little bit faster, they're spread out a little bit more. To go from solid to liquid, they need to speed up. Well, if I want to move faster, I'm going to need to gain some energy. So in order for the particles to go from solid to liquid, they have to gain energy. They have to absorb some energy. So that would be endothermic. If they have to slow down, so you're going from gas to solid. Particles are moving really fast as a gas. They're not moving very much at all as a solid, so they have to slow down. That means they have to release energy. That's an exothermic process. So when you're looking at phase changes, just think about particle motion. There was part of the enthalpy of reaction section in the notes that looked at energy diagrams. So an energy diagram just has reactants and products, or reactants and products, and it just shows whether a process is exo or endothermic. You just have to look to see, do the reactants have to absorb energy to become products, or do they have to release energy to become products? So that's all an energy diagram is really used for. And then a quick note, there was a question on states of matter for a reaction. Typically they'll give it to us. So as we're looking at reactions, they'll give us the states of matter. We don't have to worry about that. And then there are some different ways to calculate heat. We're going to look at all of the different ways, and we're going to look at how the problem is set up, what we're given, and based on what we're given and what the problem is asking for, we'll be able to see the type of setup and the type of problem that we have. So the two ways that 2.4 talked about was calorimetry and Hess's law. Calorimetry, we're going to look at both constant volume and constant pressure today. That's coffee cup and bomb calorimetry. Tomorrow we will focus on Hess's law. So I'll answer all the questions on Hess's law tomorrow. Hess's law seems a lot more complicated than it really is. It's essentially you have a system of equations you have to manipulate, add them together. So we will focus on Hess's law tomorrow. Today we're going to focus on calorimetry. That's using MC delta T. Okay, so as we look into calorimetry, there are two types of calorimetry problems. They both use the same setup. We're going to use the first law of thermodynamics. Coffee cup calorimetry, that's what the specific heat lab used. So coffee cup calorimetry is really coffee cups. I just take two styrofoam coffee cups, put them together, and my very fancy lids that I cut out of cardboard boxes. Right? This is coffee cup calorimetry. Now with coffee cup calorimetry, it's good for measuring heat flow, but it doesn't work well with gases. Because this cardboard lid with two small holes in it is not going to keep gases in the calorimeter. The reaction has to be able to occur in solution or in water, because that's what we would have in here. It also can't be used for high temperature situations, meaning like hundreds of degrees Celsius, because styrofoam melts. So we can't do combustion in here because it'll melt. Now, for any type of calorimetry, we use the first law of thermodynamics. First law of thermodynamics says that energy is neither created nor destroyed. So we use the idea that the heat of the reaction that's occurring plus the heat of the water has to equal 0. This is how we get the idea of what we used in the specific heat lab, that, for example, negative Q of metal equals Q of water. We said all of the heat that was released by the metal had to be absorbed by the water. That's due to the first law of thermodynamics. They have to add up to equal 0. So whenever you're doing calorimetry, whether it's coffee cup or bomb calorimetry, we still have Q. Q is MC delta T. So we're still using the idea we need mass, specific heat, and change in temperature. Now a bomb calorimeter is a little bit different, and I don't have a bomb calorimeter because they're fairly expensive. It's essentially a metal chamber that you can do combustion reactions inside. So you're essentially blowing things up inside this metal calorimeter. So bomb calorimetry is good for measuring gases, specifically those produced in combustion. Bomb calorimeters have a calorimeter constant. Now you will either be given that constant or asked to calculate that constant. The reason we have to worry about this calorimeter constant means that the calorimeter does absorb some of the heat. We assume that a styrofoam cup is an insulator. It's not going to absorb any heat. Metal, on the other hand, will absorb heat. So we'll look at what that means, but we just have to tie in the heat of the calorimeter into this overall equation. So sometimes we'll have extra Qs, extra heats, if we have water inside the bomb calorimeter. But again, we still look at the first law of thermodynamics. So the first thing we will always write in a calorimetry problem are all of the Qs that are involved in the calorimeter. So for the example of a bomb calorimeter, we could have the reaction that's occurring. If there's water, we have to take that into account, as well as the calorimeter. To calculate Qcal, so that's the heat absorbed by the calorimeter, Qcal is calculated by C delta T. We don't worry about the mass of the calorimeter. We only worry about the calorimeter constant and the change in temperature. And like I said, we will do more examples with this as well. So just to show you what a bomb calorimeter looks like, so we have this metal chamber, and we have some reaction that's taking place in the very center of this chamber. So again, this is a metal chamber. We have the reaction that's taking place inside. Sometimes it's surrounded with water, other times it's not. So we just have to look at what the problem is giving. But then they put this gas through combustion. Releases lots of heat. We measure that heat. We can find Q, we can find a specific heat, the delta H, but that's what a bomb calorimeter looks like. All right, so now we're going to get into some examples. So I did examples in the videos. We're also going to do some examples together. That way you can see as many examples as possible, especially then when you get into mastering. You will have lots of practice and examples to look at. So if we look at example 1, this was on page 10 of the notes. This is actually going back to 2.1 and 2.2. So this says hydrogen and oxygen gas are in a cylinder with a movable piston. When ignited, the system loses 1,150 joules of heat. So heat is Q. I'm going to label this Q. The reaction also causes the piston to rise, and 480 joules of work, okay, so work I know is W, is done as this piston is pushed against the atmosphere. What is the change in internal energy of the system? Change in is delta, internal energy is E, so we're looking at delta E. So that's why this is going back to videos from over the weekend. The only thing you need to know about delta E is how to calculate it using heat and work. So delta E equals Q plus W. Now the biggest thing with this example is knowing what the signs of Q and W are. So if the system loses 1,150 joules of heat, what's the sign for Q? Negative. So negative 1,150 joules is Q. Now work is a little bit more difficult, but it says that the piston rises, which means work is being done on the system. The system is this piston that can move. So if work is being done on the system, energy is going into the system, this will stay positive. So this is using the idea that we have to think about what is the sign for Q, what is the sign for W. The only thing you really have to ever do with work is just know what the sign is based on is work being done on the system, or is it being done by the system? If it's being done on the system is gaining energy through work, it's going to be positive. So if we do negative 1,150 plus 480, I got negative 670. Energy is joules. So again, Q is negative because it's losing heat. Work is positive because it's being done on the system. Questions on this first example? Okay, so then we will look at example 2. So example 2, the specific heat of ammonia is 4.381 joules per gram Kelvin. Now before I even move on, joules per gram Kelvin and joules per gram degree Celsius are the same thing. That can be used interchangeably because delta T, whether it's in Celsius or Kelvin, is actually the same thing because you always do conversions before you find the change in temperature. So water's specific heat is 4.184 joules per gram degree Celsius and 4.184 joules per gram Kelvin. So they are the same thing. So the specific heat of ammonia is 4.381 joules per gram Kelvin. So specific heat is C. Calculate the heat required. Right, so heat is Q. I just go through and label everything. So required to raise the temperature of 1.5 grams of ammonia from 213 Kelvin to 218 Kelvin. And then the second part of the question is looking at molar heat capacity. So we'll look at that second. So the first part of this problem is calculate Q. Now this isn't even a calorimetry problem that we have to worry about. There isn't. It's not two things inside of a calorimeter. All we're doing is focusing on ammonia. So if I have Q, M, C, I probably have delta T. I'm just going to use Q equals MC delta T. Or as many people say, MCAT. So I'm solving for Q. That's my variable. I'm going to leave that alone. The mass of ammonia, 1.50 grams. Specific heat, 4.381 joules per gram Kelvin. And then delta T. How do you always calculate delta T? Final minus initial, right? It's always final minus initial. So then you just have to be careful. If it's going from 213, that's my initial, to 218, that's the final. Final minus initial, 218 minus 213. Delta T is 5 Kelvin. Now I put all the units here so you could see how things cancel. I have grams here, grams on the bottom, Kelvin here, Kelvin on the bottom. I'm left with joules. So 1.5 times 4.381 times 5. And I think 3 sig figs. I got 32.9 joules. 32.9 joules. So when you're looking at the problem, just look at what you're given. If you're given a specific heat, there's nothing else you can do except for MC delta T. Now the second part of this asks for molar heat capacity. So this is going to allow us to look at the difference between specific heat and molar heat capacity. I'm going to start with specific heat. I'm just going to write it out. 4.381 joules per gram times Kelvin. Specific heat is 4.381 joules per gram times Kelvin. That's specific heat. Molar heat just means instead of grams, we should put in moles. And so what that means is I want to cancel out the grams and put moles in its place. Now, ammonia might be in a formula that you're not as familiar with yet. Ammonia is NH3. Ammonia is NH3. The reason I'm telling you that is because we need that to plug in some numbers here. How do I go between grams and moles? What do I need? And I can hear people plugging in. I need to plug in the molar mass. So nitrogen is 14.01 plus 3 times 1.008. .034 grams is the molar mass of ammonia. Again, the reason that I needed molar mass here is because molar heat capacity is joules per mole times Kelvin. So this allows my grams to cancel and give me joules over Kelvin and moles. So times 4.381. 74.6. Let's do one more. Let's do 74.63 joules per mole times Kelvin. So specific heat is how many joules does it take to heat 1 gram by 1 degree Celsius. Molar heat capacity is how many joules does it take to heat 1 mole of a substance by 1 degree Celsius or 1 Kelvin. So it's just the units. I put that on there because there are some questions on mastering like this. Questions on this example? All right, so now we're going to look at the difference really between Q and delta H. So if we look at example 3, this says 2.15 grams of methane. Methane is CH4. Is combusted to form carbon dioxide and water. Okay, so we have a reaction that's taking place. All of the heat evolved is used to raise the temperature of 100 grams of water by 17.8 Kelvin. Calculate the heat of combustion per mole of methane. Now, in this example, I have 2 systems. I have 2 focuses. I have methane and I have water. So that means that I have Q of methane. Methane again is CH4. So I have the heat of methane that I have to worry about. And I have the heat of water. I have 2 systems in this problem. So every heat has to add up to equal 0. The first law of thermodynamics says that the methane plus the heat of the water add up to equal 0. So one of them is going to lose heat, one of them is going to absorb heat. Using the first law of thermodynamics, this helps us so we don't forget negatives anywhere. Now, I'm going to go through again. So it gives me an amount of methane. All the heat evolved is used to raise the temperature of 100 grams of water by 17.8 Kelvin. Calculate the heat of methane. So I'm calculating Q of methane. I'm going to leave that alone. I'm going to leave that alone. That's what I'm solving for. Which means I should be able to plug information in for Q of H2O. Q is M times C times delta T. All of these variables need to describe the water. You could rearrange the equation like right now if you wanted, but again, I'm just going to wait. So again, I'm solving for Q of methane. I'm leaving it alone. What was the mass of water given in the problem? We have 100 grams. Now, it didn't give us the specific heat of water. That's because we need to know the specific heat of water. Any other specific heat you'll be given, we want to know the specific heat of water. C of H2O, 4.184 joules per gram degree Celsius, or joules per gram Kelvin. They're the same thing. So 4.184. Now the delta T, they actually gave us the delta T here. Because it says that we're raising the temperature by 17.8 Kelvin. That is the delta T. So, we have, again, I'm leaving Q of CH4 alone. 100 times 4.184 times 17.8, 7447.52. I probably should put a unit. That's joules. Q is always in joules. So what we're doing right now is we are solving for Q. Now, how do I just get Q of CH4? How do I rearrange the equation? I say Q of CH4 equals, this is just algebra, subtract this to the other side. Negative 7447.52 joules. Now, we're not quite done. Q is my amount of heat, in this case released, for a specific amount of substance. So this, use a different color. This heat, negative 7,447.52 joules, was per 2.15 grams of CH4. So 7,000 joules of heat was released for 2.15 grams. This wants us to calculate the heat per mole. So instead of joules over grams, it wants joules over moles. Here's where the difference between Q and delta H comes into play. This is Q. Q is negative 7,447.52. Box your answer, there it is. But delta H wants us to put it in joules per mole. So it's just one extra step. To go between grams and moles, we need the molar mass of methane. So 12.01 times 4 times, nope, not times, plus 4 times 1.008. So the molar mass of methane is 16.042 grams. Again, this is the molar mass of CH4. This is the difference between Q and delta H, this one calculation right here. So times negative 7,447.52 divided by 2.15. Ooh, that is a large number. Negative 55,569 joules per mole. Or you could make it a little bit easier to work with. Put it in kilojoules. Kilojoules, you just divide that number by 1,000. Negative 55.569. It doesn't specify joules or kilojoules, so whichever one you use is okay. But this is the difference. Notice we still are calculating, even though this is delta H, we still calculate Q first. But this is the amount of joules per specific amount. Then you just have to go to joules per mole for it to be delta H. Okay, questions on this example? Okay, so we're going to actually skip example 4 for now. We're going to do example 4 next week. That's solution calorimetry. So then we're going to go to example 5. Right, example 5 is the last example that we're going to look at out of this part of the notes. Example 5 is a bomb calorimetry question. So I'll put example 5 up here and read through while I'm erasing the my eyes. So the combustion of methyl hydrazine, which is CH6N2, that's rocket fuel. Right, produces N2, CO2, and H2O. It gives us the reaction right here. And it says when 4 grams of methyl hydrazine is combusted in a bomb calorimeter. Okay, so we know it's bomb calorimetry. Doesn't actually matter what type of calorimetry it is. The process is the same every single time. The temperature of the calorimeter increases from 25 to 39.5 degrees Celsius. In a separate experiment, the heat capacity of the calorimeter is measured to be 7.794 kilojoules per degree Celsius. Calculate the heat of reaction for the combustion of a mole, CH6N2. So there's a lot to kind of unpack in this problem. First, calculate the heat of reaction. That means we want delta H of reaction. All that means is our answer should be in kilojoules per mole. That's all. It's calculated the same way. If it's calorimetry, we're always calculating Q first. So they tell us 4 grams of this rocket fuel is combusted. Temperature of the calorimeter increases from 25, that's initial, to 39.5 degrees Celsius. They also give us the heat capacity of the calorimeter. So that's labeled as CCal. Now this is calorimetry. It still follows the first law of thermodynamics. Which means I need to see what are the different systems that I have in this calorimetry problem. Well, one of them is the methyl hydrazine. So I'm just going to label this, I'm going to label this as reaction. It's the reaction that's taking place. So one of the systems is this reaction of methyl hydrazine. That's one of my systems, right? Is the reaction of methyl hydrazine being combusted. It says nothing about water in this calorimeter, so I don't worry about it. That means there's no water in here. The only other thing that I have to worry about in this calorimetry problem is the heat that is absorbed by the calorimeter, because it gives us a calorimeter constant. If it would not have given us a calorimeter constant, we wouldn't have to worry about it. But because it gives us the calorimeter constant, we have to take into account the heat that is being lost to the calorimeter. So the first law of thermodynamics just says the heat that is produced by the reaction plus the heat from the calorimeter add up to equal 0. There are no other systems in this calorimeter. Now I'm solving for heat of reaction. So I'm leaving Q reaction alone. Leaving it alone. That's what I'm solving for. Now to calculate Q cal, it is not the same as Q of water. Q cal is simply C cal times delta T. To calculate the heat absorbed by the calorimeter, it is just the calorimeter constant times delta T. So I'm going to plug in C cal. Just be careful with your units. Just always double check your units. 7.794 kilojoules per degree Celsius. We said delta T is always final minus initial. So over here to the side, I'll just put final minus initial. 39.5 minus 25. 14.5 degrees Celsius. So if I take a look at this, my degrees Celsius cancels. I'm left with kilojoules. This is why I just said be careful with units. You don't have to convert. Just be careful with the units that you get out of the problem. So Q reaction plus 113.013 kilojoules equals 0. So what's Q reaction? That's going to be my value for Q reaction. How do I... Should just move this over to the other side. Subtract 113.013 to the other side, so it's just negative. Now this is Q. Heat of reaction is per mole. Q is for this amount of methylhydrazine. 113 kilojoules is released when 4 grams of methylhydrazine is used. We don't want kilojoules per gram. We need to go from grams to moles. I'll give you the molar mass right now. 46.078. Again, that's the molar mass, CH6N2. So my grams cancel. Now I have kilojoules over moles. I got negative 1302 kilojoules per mole. This is delta H. The only difference between Q and delta H is the units. Q is just how much heat is released when 4 grams is combusted. Delta H wants to know what is the heat of reaction per mole of this reactant. All right, so I want to go through one more, I guess, example together. This is number 5 on page 13. So this is part of the calorimetry practice, but I wanted to go through it together because it asks for final temperature. It also is a little tricky when it comes to finding the mass. And so I wanted to go through this, and then you'll have time just to move around to work together to practice. So it says an iron sphere of diameter 4 centimeters and density of 7.86 grams per centimeter cubed at 20 degrees Celsius is dropped into a perfectly insulated beaker containing 90 grams of water at 50 degrees Celsius. The specific heat of iron and water are 0.45 and 4.184 joules per gram Kelvin, respectively. So that means this is H2O, this is Fe. What is the final temperature in degrees Celsius of the iron sphere? Okay, so let's start by figuring out what all of our systems are in this calorimetry problem. We know it's calorimetry because we have one thing being put into a container with something else. So if I think about my two systems, I have an iron sphere, so QFE, and I have water, QH2O. It doesn't say anything else about a calorimeter constant, just iron and water. Now instead of solving for one of the heat values, we are solving for final temperature. Now the final temperature of the iron, if it's in the same container as the water, the final temperature of the iron is also the final temperature of the water. So I'm going to just write out what Q equals. So Q is mass of iron, specific heat of iron, delta T, plus MC delta T of H2O. Now my goal is to solve for part of the delta T variable. So over here, off to the side, I'm going to have to do some more. This is going to be lots of algebra. So I need another mass of iron. Well, it doesn't give me the mass of iron. Instead, it gives me the diameter and the density. Well, density, you remember density is mass over volume. So density is a way that I can solve for mass, but I would need the volume. Here is where, if you're in college calc, Ms. Bergman would be very proud. The volume of a sphere. Now, I always get the question like, wait, do I need to know these volume equations? No, but like this could be like a potential mastering type of question, which is why I wanted to do it together. Volume of a sphere is 4/3 pi r cubed. That's the volume of a sphere. So 4/3 times pi. Now if the diameter, here's a circle, diameter is all the way across, that's 4 centimeters. What is just the radius? What's half of 4? 2. So to calculate the volume of this sphere, we do 4/3 times pi times 2 cubed. 2 cubed is 8. 8 times pi times 4/3 is 33.5 centimeters cubed. There's volume. So the volume of this sphere is 33.5 centimeters cubed. The density, 7.86 grams per centimeter cubed. So the mass is density times volume, 7.86 times 33.5. So it's all this background just to get the mass of the iron sphere. That is 263.39 grams. That is the mass of Fe. Oh, I just wrote that. So the mass of iron, 263.39. What was the specific heat of iron that we were given? Right here, 0.45. Just in general, how do we calculate delta T? Delta T is what minus what? Final minus initial. I don't know final, so I'm going to label it T final. What was the initial temperature of the iron? 20 degrees Celsius. So here is Q of Fe, MC delta T. Plug in the variables for water. 90 grams of water. Specific heat of water. Remember, it doesn't matter whether it's joules per gram Kelvin or joules per gram degree Celsius, they are one and the same. Now again, delta T is final minus initial. I don't know the final. Final temp of both is the same because they're in the same container. Initial temp of water is 50 degrees. Now this becomes a giant algebra problem. So, I'll show you how I did it. If you had a little bit different of a way of doing it, that's fine. But I started by multiplying what I could multiply. So I did 263.39 times 0.45. Got 118.53 times TF minus 20. I did 90 times 4.184. 376.56 times TF minus 50. Try to not do too many things at once, just so that way I know, like I could see if there's ever a potential mistake. So I just multiplied the two terms in the front. Now I can distribute. All right, so I'll distribute 118.53 to TF into 20. I'll distribute 376.56 to TF into 50. So I get 118.53 times TF minus, I'll multiply 118.53 by 20, 2370.52, plus, I'll distribute the other terms, 376.56 times 50, 18828. That whole thing equals 0. Now we can combine like terms. I have two TF terms. I have two just integer terms that I can combine. So it was 495.09 times TF minus 21198.52 equals 0. You can move the 21,198 over to the other side. And then I can divide to find TF. So once you had it set up here, it just became a huge algebra problem. When you solve for TF, 42.8 degrees Celsius. So this is just using the idea that TF is the same for both. Solving for TF is probably one of the most complicated problems, only because it's lots and lots and lots of algebra. Okay. So, no, not that one. Next slide. All right, so for the rest of class, this is, quite difficult to read right now, but you're just going to have time to work with a partner, or you can work on your own if you want, on the calorimetry practice. It's not 10 and 11, it's 12 and 13. Pages 12 and 13, where we're at right now. So 1 through 4 on the front, mostly conceptual with a little math. Then page 13, you just have 6, 7, and 8 to look at. I have the answers up here on the board. I also have the answers linked right here. And so if you'd rather just have the answer key kind of up on your Chromebook in front of you. But then after completing the practice, you can work on mastering, you can work on post-lab, but the reason that we're going through the practice is, one, so that you can ask